Mercy, Urani, Gilcrease. Lucky is here. Luna,
Here.
Macias. McKinnon is here. Morris.
I'm in the Zoom.
Oh, Macias is here? Oh,
Yes.
okay, I see you. Powers, Renfrew, Salvador, and Spivey's here. All right. Okay, so we're going to continue our discussion of equilibrium. And what we're going to look at next is situations where an equilibrium system involves pure solids and liquids. So let me bring up, oh, almost forgot. Let me share my screen first with those guys out there in Zoom. And let me go to PowerPoint. Okay, so let's talk about situations where you have solids and liquids involved in an equilibrium system, and how do we deal with that, all right? So first thing we're gonna say is that when it comes to solids and liquid substances involved, their concentrations do not change in any chemical reaction, all right? And the reason for that, I can show you mathematically. Well, let me see. Okay, let me just show you here and then I'll erase it so you can write it down quickly. So concentration of anything would be moles of that thing divided by the volume it occupies, right? Now, the thing about moles is that we know that the molar mass of a substance is equal to the mass in grams divided by the moles of the substance, right? So if I were to replace mole with, well, mole would be equal to grams over the molar mass, right? So if I were to replace mole with this combination right here, I'm going to end up with grams divided by volume multiplied by the molar mass, all right? Now, the thing is, the grams divided by the volume is known as the density. So we can rewrite this as density divided by the molar mass, all right? So if you look at this equation carefully, right? And this is for solids and liquids, right? You'll see that basically the concentration of a solid or liquid would be equal to the density of that solid or liquid divided by the molar mass. Now, the molar mass is always constant, right? That doesn't change, right? And the density for solids and liquids doesn't change by much, right? In fact, most times you just assume it to be constant at normal temperatures, right? So basically what this means is that you're going to have a constant divided by a constant, which means that the concentration of a solid or liquid is constant, right? So the point here is that when it comes to solids and liquids involved in any chemical reaction, its concentration doesn't change. That is not true for solids and liquids. Not true for gases or solutions, right? Concentrations can change more dramatically in those situations, but for solids and liquids, the concentration remains constant. So that's what we take into account when it comes to determining how solids and liquids are involved in an equilibrium system. All right. Is it okay for me to erase this? All right. I just thought I should show you that, so that explains why the concentration of a solid or liquid doesn't change, right? So basically what we're saying here is that even though you might have the amounts of solids and liquids changing as a system goes from before equilibrium to equilibrium, the concentration themselves doesn't change for a pure solid or liquid. So for example, if you look at this reaction here where calcium carbonate is being decomposed to form calcium oxide and carbon dioxide, right? We have two solids here and we have a gas right here, right? Well, when we're writing the Kc expression, instead of doing it the way that we would normally do, where we take the product of the concentration of the products and divide it by the products of the concentration of the reactants. Instead of writing it this way, we only take into account any gases or aqueous solutions involved, right? We don't include solids or liquids in writing down the equilibrium expression. So in this case here, Kc would simply be equal to the concentration of CO2. And the same is true for Kp. If you remember, Kp is the equilibrium constant expressed in terms of gas pressures. So basically, if we were to write Kp for this, Kp will be equal to the pressure of CO2, and that's it, all right? So that's how we deal with solids and liquids. Basically, what it comes down to is that we ignore them when it comes to writing down the equilibrium expression for any reaction involving solids and liquids. But you have to take into account, of course, gases and aqueous solutions, all right? Okay, so let's look at this example. So they gave you this reaction, carbon, which is a solid. And by the way, this underscores the importance of paying attention to the state symbols given in equations, right? Okay, so this example says the reaction of steam and coke, which is a form of carbon, produces a mixture of carbon monoxide and hydrogen called water gas, and that's the equation given for the reaction. So the question is asking for you to write down the Kc expression for this reaction, right? So Kc in this case, remember we don't take into account this when we're determining the Kc expression. So the Kc expression for this would be the concentration of CO times the concentration of H2 divided by the concentration of H2O. And that's it, all right? So that's how you write the Kc. And if the question was asking for Kp, well, Kp would be equal to the pressure of CO times the pressure of H2 divided by the pressure of H2O, all right? Just in case you're asked that, all right? Okay, so that's basically how we deal with solids and liquids. We simply ignore them when writing down the Kc or Kp expression for the system in equilibrium where a solid or liquid is involved. All right, any questions so far? Any questions? Any questions? No questions? Okay, so let's talk about how do we interpret the equilibrium constants, right? What do they tell us about the particular system that is involved, all right? So the first thing I'm going to say here is, as soon as I can, okay, good. If the Kc or Kp, or for that matter, any K, because you're going to meet some other Ks later on, right? But for now, if the Kc or Kp values are extremely large, what that tells us for the reaction or for the system is that you have more products, much more products compared to the reactants, right? And in fact, if the reaction goes to completion, then basically Kc or Kp would be infinity, right? If you think about it, it makes sense because remember Kc is equal to basically concentration of products over concentration of reactants, right? So if you have products but no reactants, then basically Kc or Kp would be infinity or very large, all right? Another thing we can say is that the inverse is true. If Kc or Kp is small, that means basically that the reaction favors the reactants and you have little products, all right? Another thing too, very important, especially in light of what we're going to look at next, the Kc value or Kp value only applies to systems that are in a state of dynamic equilibrium, right? So in other words, if the system is not in equilibrium, then the concentration values cannot be used to calculate Kc or Kp, right? And just to remember what we mean by equilibrium, when we're talking about a system in a state of dynamic equilibrium, we're talking about a system where the rate of the forward reaction is equal to the rate of the reverse reaction, all right? So unless that condition is in place, the Kc or the calculation of any Kc or Kp value based on the concentrations or pressures will simply not be accurate in terms of determining the Kc value. You will be determining something else, which we're going to talk about shortly, if you use non-equilibrium values for concentration or pressure. Okay, so what else? And this here line talks about the difference between a reaction being thermodynamically favored as opposed to kinetically controlled. This is important, especially again for those of you who have to do organic chemistry. Basically, you have to understand that basically there are two things that chemists oftentimes take into account: whether or not the reaction is feasible in terms of forming products and how fast the reaction goes, right? We talked about kinetics in the previous chapter. Kinetics deals with how fast the reaction goes, and thermodynamics, under which equilibrium constants and all that comes under, basically determines whether or not the reaction will be favorable in terms of going forward from reactants to products, right? And the key thing you need to remember is that it is possible that a reaction is thermodynamically favored, but kinetically speaking is very slow, right? In other words, okay, you know that this reaction is going to take place, but it may take a long time, right? So the point I'm getting at here is that there is no necessary correlation between how fast the reaction goes and whether or not the reaction will take place, right? Those are two separate things, all right? There are some instances, for example, I'm thinking of one reaction that you're going to meet in organic chemistry, where by simply altering the temperature, you can favor the more stable product as opposed to the one that is formed faster, right? If you lower the temperature in this particular reaction, if I remember correctly, the more stable product will be formed. No, the less stable product will be formed, but the one that's formed faster will be the major product. And then the reverse would happen if you increase the temperature. So, you know, those are some things that, you know, whenever people are doing reactions and doing their research, they take those two factors into consideration. Okay, so let's look at this example. It gives you a balance equation. In fact, this is the reverse of the reaction I think we looked at. Anyway, I don't remember. Anyway, so they gave me this equation here, and the question is asking, is this reaction likely to occur to any appreciable extent at 298, where Kp is equal to 5.33 times 10, and this should be raised to the 22 here, all right? So basically, what we're saying is that Kp for this reaction would simply be equal to 1 over the pressure of CO2, because again, we ignore the calcium carbonate and the calcium oxide when writing down the Kp expression because they're solids, right? So basically Kp would simply be equal to 1 over P C over 2, which is equal to 5.33 times 10 to the 22, right? So what that means is that the pressure of CO2 will be equal to 1 over 5.33 times 10 to the 22, which I would expect to be a very small number. Let's see, so 5.33 times 10 to the 22, and then I put that under 1. So when I did that calculation, I got 1.88 times 10 to the 22, right? So that would be 10 to the minus 23, minus 23. So that would be the Kp value. So what that tells you is that the reaction favors the products heavily because you have very little carbon dioxide because the pressure of the carbon dioxide, which would be in atmospheres here, is very low, right? So therefore, what that tells us is that the reaction lies heavily on the product side, on the right side of the equation, all right? Okay, any questions about this? Any questions? Any questions? Okay, moving along. So now we're going to get into what is called the reaction quotient, right? Now the reaction quotient is very similar in terms of the mathematical expression. It's very similar to the equilibrium constant, but there's one important exception, right? And that exception is that the concentration terms are not necessarily at equilibrium, all right? So as stated here, for non-equilibrium conditions, the expression having the same form as Kc or Kp, we call that the reaction quotient. And in the case of concentrations, that would be Qc. In the case of pressure terms in the equation, that would be Qp, right? And that would be the ratio of the products to reactants at any time. So this could be equilibrium as well as not equilibrium, right? So basically, if you have an equation and you write down the expression where you have the concentration of the products as a numerator divided by the concentration of reactants as a denominator, right? At any time, we call that the reaction quotient, all right? And that's important for predicting certain things, which we're going to get into shortly, right? In fact, as stated here, the reaction quotient is not constant because Kc is basically, and Kp are constant at constant temperature. But Qc and Qp are not necessarily constant, right? The only way it's constant is if Qc or Qp is equal to Kc or Kp, right? But because Qc or Qp is basically determined at any time, including equilibrium, then basically that cannot be constant, all right? But it can be used for making predictions as to which direction the reaction will shift in order to achieve equilibrium, all right? And we're going to see how that works shortly. Now, how do we do that actually? So basically what we do is we compare the QC value to that of the KC value, all right? Now, if QC, and this chart here basically explains how we make that prediction. If QC is less than KC, as you can see in this case and this case here, if QC is less than KC or if QP is less than KP, then what that means is that the amount of product compared to the reactants is small, especially compared to what is needed for equilibrium to be established, right? So basically what's going to happen is that there's going to be a net shift in the reaction towards the product side, right? So therefore the concentration of the products will increase and the concentration of the reactants will decrease, and that will continue until QC or QP is equal to KC or KP, right? And that is where equilibrium will be established, right? So if Q is less than K, right, that is not equilibrium. So the system will try to establish equilibrium by pushing the reaction forward to form more products, which means that Q would start increasing, the amount of reactants would decrease, which would also make Q increase, and that will continue until you get to equilibrium where Q is equal to K. When Q is equal to K, then the system is in a state of equilibrium. Now, what if it's reversed? What if Q is greater than K, as shown here and here, right? If Q is greater than K, what that means is that the amount of products that you have there is too high compared to the amount of reactants, compared to the amounts required for equilibrium. So basically what's going to happen in that case is that the reaction is going to shift. The net reaction is going to shift to the left. In other words, some products will react so as to decrease its concentration here in the numerator, and at the same time, the concentration of the reactants will increase, and that will continue until you get to a situation where Q is now equal to K, and again, the system will be in a state of equilibrium, all right? So that's the utility of determining QC or QP, right? If you're given a question where you're given, let's say, some concentration terms for different components, and there are a couple of examples in the assignments we're going to look at. What you do first is calculate QC or QP, and then compare that to the given KC or KP value, right? If Q is less than K, the reaction is going to shift to the right so that Q is increased so that it's equal to K, and therefore the system is at equilibrium. If Q is less than K, then the reaction is going to shift to the left, and therefore, as a result, the Q will be lowered so that it's now equal to the K, and therefore the system will be in a state of equilibrium. So that's basically how we use the reaction quotient to make that kind of prediction, all right? Okay, so this is very important for you to grasp. Any questions about this? Any questions? Any questions? All right, so let's go to the assignment. And I have some extra copies of the assignment just in case, you know, somebody might need. Okay, so could you pass this on to me? Anybody else? Anybody else? Okay. So let me go to assignment number 3. Oh. Okay, so now we're going to look at question number. I think we. Oh, by the way, did we do 3? I can't remember. Did we do question 3? No? All right, let me do 3 quickly. I'm just going to do the first 2. You should be able to do the others, right? Okay, so the equation that you're going to need for question number 3 is Kp is equal to Kc times RT raised to the delta N, right? So basically R is molar gas constant, T is the temperature in Kelvin, and you remember what delta N is? Delta N is what? Can anybody tell me? Delta N is the change in what? Or what is delta N? The difference in the total sum of the coefficient of the product and the sum of the coefficient of the reactants, right? So it's products minus reactants, right? Okay, so the question is asking for you to express Kc in terms of Kp. So in other words, you need to rearrange this equation for each of these reactions, but you need to rearrange this equation So that means that KC is equal to KP times RT to the minus delta N, all right? Because the question says express KC in terms of KP, all right? So in this particular reaction for A, KC would be equal to KP times RT, and delta N would be, well, the sum of the coefficients here is 2, the sum of the coefficients here is 3 plus 1, 4, so that would be 2 minus 4, so the answer would be KP RT to the minus 2, and that would be the answer for the A part, all right? Any questions about that? Any questions? Okay, what about B? How would you, based on what we just did, how would we do B? KC would be equal to KP times RT. So my question to you is, what is delta N in this case? Oh, shoot, I made one mistake here, I'm sorry. I forgot to include the minus sign here. So this should be minus, which would mean that this should be plus, okay? So please make that change. I'm sorry about that. So this should be squared, all right? Okay, so this will be minus delta N. So my question to you is, what is delta N in this case? It will be 3, 2 plus 1, 3 minus 2, right? So this works out to be KP times RT raised to the minus 1, all right? And that's basically how you do the others. I'm sorry?
Don't you need to distribute the negative?
No, you can leave it like that. Or another way of writing this would be KP over RT. Or KP, you're talking about this, R to the minus 1, T to the minus 1. Yeah, that is correct too. I mean, they're just different ways of saying the same stuff. All right? Okay, any questions about this? Any questions? Any questions? All right, so what I really want to get to, let me clear this here. I want to get to the next, oh, sorry, yes, ma'am.
Shouldn't it be negative 2 then? On the A, since.
No, because this will be 2 minus 4, that's minus 2. And then the negative sign makes that plus 2.
Okay.
All right? We have the 9 minus sign here, 3 minus 2, that's 1. That makes a minus 1. All right? Okay, let me clear this here because I want to get to the next question, which deals with the reaction quotient and how we can use it to make predictions as to which direction the reaction will shift. So here is a question which deals with that very topic. They gave you the balance equation, and it says here at 500 degrees Celsius, the equilibrium constant for the following reaction is 0.080. So this here is the Kc value. So this here is the Kc value. So it says, given that the concentration of ammonia is that, concentration of nitrogen is that, concentration of H2 is that, find Q, which is reaction quotient. And this Q will be QC. So QC is equal to the concentration of ammonia squared divided by the concentration of N2 times the concentration of H2 cubed, right? And then we put the numbers in. So they gave us the values for ammonia. Ammonia is 0.0596. This would be squared divided by the concentration of nitrogen, which is 0.600, multiplied by the concentration of H2, which is 0.420, and this will be cubed, all right? So let me work this out, and please work this out with me, just in case I'm wrong. So 0.0596 squared divided by 0.6 divided by 0.42, and this will be cubed. And according to my calculations, this works out to be interesting. 0.0799. Anybody else got that? Okay, so that's QC. So what we do next is compare QC to the given KC value, right? And the question you have to ask yourself is QC greater than or less than? And as I can see here, QC is slightly less than KC. I'm going to put here slightly in parentheses because there's not much daylight between 0.799 and 0.08. All right. So what does that mean? If QC is less than KC, what that means is that the reaction will shift to the right. Right? The reaction will shift to the right so that QC will increase to be equal to KC, and then the system will be in a state of equilibrium at that point. All right? And it will be a slight shift because of the closeness between the KC and the QC value. All right? Okay, any questions about this one? Any questions? Any questions? Any questions? Any questions out there in Zoom? Okay, so let me clear this, if that's okay. Can I clear it? All right, so let me clear this. And scroll down to the next question. Let me see what it says here. Okay, so it's another QC type question. They gave you the equilibrium constant. So this again is KC. So this here is KC right here. And they gave you the different concentration terms, and they're asking for you to calculate Q. So again, Q will be equal to the concentration of H2 times the concentration of CO2 divided by the concentration of CO times the concentration of H2O, all right? And then we put the numbers in. So for H2, what's H2? H2 is 0.42, CO2 is 0.37, divided by CO, what's CO? 0.15 times H2O, which is 0.25, all right? So let's see what that gives. 0.42 times 0.37, and then divide that by 0.15, and then divide that by 0.25. So according to my calculation, again, please check to make sure I'm doing the right thing, but what I got is 4.1, all right? So I got 4.1. Okay, so my question to you is, what's the next step? Because remember the question is asking how the reaction will proceed. In other words, which direction will the reaction shift in order to achieve equilibrium, right? So how would you, based on the fact that we have determined that QC, this is QC, is equal to 4.1, then what do we do next? Now that we have QC, what do we do next? Compare to KC, right? KC is 5.1, QC is 4.1, so QC is less than KC, right? So which direction will the reaction shift in order to achieve equilibrium? To the right, exactly. So reaction will shift to the right to achieve equilibrium, all right? And that's it. All right, any questions about this? Any questions? Any questions? No questions? Okay, so let me clear this. If that's okay, that's okay, okay. And let me scroll down. Keep having any other related. Okay, so that's it as far as those types of questions are concerned. So let me get back to the PowerPoint. And now we're going to get into what is a very important principle when it comes to equilibrium systems. And if there are any French speakers inside here, let me apologize ahead of time because I'm sure I'm going to massacre this person's name. I think the correct pronunciation is something like Le Chatelier. So I'm trying to stick to that, but you know, sometimes I'll fall back to just saying Le Chateliers. But this is a principle that basically helps you to make predictions as to how a system in equilibrium will respond when you make certain changes to it, right? So if you look in different textbooks, you see that this principle, the Chatelier's principle, is expressed in different ways, right? So this is one way of expressing it. I'm quite sure in your textbook, you'll see the verbiage, you know, be different, but It's different ways of saying the same thing. So let me just read what it says here. It says, when any change in concentration, temperature, pressure, or volume is imposed on a system at equilibrium, the system responds by attaining a new equilibrium condition that minimizes the impact of the imposed change. So that's a bit wordy. The way I like to put it in my own words is that if you have a system already in a state of equilibrium, right, and you make a sudden change to that system, which disturbs the equilibrium, then the system will respond by counteracting the change that you are imposing, right? So whatever you're doing to the system to disturb the equilibrium, the system will respond by doing the opposite in order to reestablish equilibrium, right? So we're going to see an example of this. So for example, if you, for example, let's say, increase the concentration of one substance in the system already at equilibrium, then the system will try to decrease the concentration of that substance in order to achieve equilibrium. Whatever you do to the system to disturb the equilibrium, the system will try to do the opposite in order to restore equilibrium, right? That's basically my way of looking at it. I don't know if that helps, but that's the way I explain the Chandler's principle. All right, so what we're going to look at are four factors, right? How four factors change, if there's any change, changes the system, and then how the system will respond, right? And the first one is basically changing the amount of a reacting species, right? Now, remember, at equilibrium, QC is equal to KC, right? Now, if you change the concentration of, let's say, a reactant, right, that will change the value of QC, right? In fact, it's going to, well, in this case, you're increasing, right, the concentration of reactant, which means that because the concentration is in the denominator of the equation, that means that Kc will decrease, right? So Kc will now be less than QC. So the question now becomes, well, how will equilibrium be achieved? Well, what will happen is that the reaction will shift in such a way that QC will increase so that it's now equal to Kc. And the way that happens is that some of the reactants must react in order for Q to increase so that it's equal to Kc, and therefore equilibrium will be restored. So basically, in this particular case, if you increase the concentration of one of the reactants, then basically the net change or shift will be from the reactants to the products in order to restore equilibrium, and therefore Q will be equal to K in that particular situation, all right? So that's basically what Le Chatellier's principle actually predicts, right? You are increasing the concentration of one reactant, the system will respond by decreasing the concentration of that reactant in order to maintain equilibrium. And here's an example of this. Now, the equation for this reaction, let me write it up top here. It's a reaction between acetic acid, which is CH3COOH, with a compound known as 1-octanol, and the formula for this, it's rather long, CH3, CH2, and then there's 6 of those units, and then CH2, actually, try to abbreviate it as much as possible. I'm just going to put CH2 and 7 of those units, and then OH, right? So this reaction will take place in the presence of acid. You're going to have an equilibrium established, and the products of this reaction would be CH3, CH2. Yeah, this is some organic chemistry, which will be in your future if you have to do organic chemistry. Make a mistake again. And then O, C, CH3 plus water. All right, so this is the system we're talking about here, right? So what this graph represents, on the y-axis, you have concentration of the different substances involved, and the x-axis represents time, right? So what this is showing you at the beginning, time 0, you have a certain amount of acetic acid, you have a certain amount of this compound, which is known as 1-octanol, right? This is acetic acid, this is 1-octanol, and then they're going to react, right? So as their concentration falls, as the reaction takes place, of course, what happens is that the product starts to form, right? So the concentration of the water and this compound, which is known as octyl acetate, will start to increase. And that continues until you get to equilibrium, right? Where the concentrations level off because now you have the rate of the forward reaction equal to the rate of the reverse reaction. So this flat line here represents the equilibrium region, the times when the system is in a state of dynamic equilibrium where the concentrations of everything is constant, right? So at this point in time, what this person decided to do is to add some acetic acid all of a sudden to the system already in equilibrium. So what happens immediately when the acetic acid is added is that the concentration of the acetic acid increases, right? So the question now becomes how the system will respond. Well, according to Le Chatelier's principle, the system will respond by trying to decrease the concentration of the acetic acid, right? So what you're going to see is that the system will respond by reacting some of the acetic acid here with some of the 1-octanol. So you see the concentrations of the acetic acid and the 1-octanol decreases. And simultaneously, at the same time, you have the concentrations of octylacetate and water increasing. And then you get to a new state of dynamic equilibrium where, again, the concentrations of the different substances remain constant, right? So basically, this demonstrates how changing the concentration of one component, right, how that affects the equilibrium system. All of a sudden, the concentration of that particular component increases, and then the system responds by decreasing the concentration of that component by shifting in the direction which favors the reaction of that component towards the other side. And therefore, you achieve a new state of dynamic equilibrium, all right? So that's basically an example, and this is true pretty much for any system that is in a state of dynamic equilibrium, all right? Okay, so that's that as far as how Le Chatelier's principle, how that principle helps you to make predictions as to how the concentration changes affect the equilibrium of the system, all right? And conversely, going back to, conversely, let's say, for example, you have some way of removing acetic acid from the mixture, right? So the system is at equilibrium already, and let's say you find some way of removing the acetic acid from the mixture. Then according to Le Chatelier's principle, the equilibrium will shift in the other direction, right? Because whatever you do to the system, which would be decreasing the concentration of the acetic acid, the system will try to replace it. The system will try to do the opposite of what you're doing. So therefore, the equilibrium position will shift in the direction favoring the formation of the acetic acid, which means that it's going to shift in this direction in order to the left, in order to favor the formation of acetic acid, all right? Okay, so here's an example. Again, this is the same reaction right here. It says here water can be removed from the equilibrium mixture by using a solid drying agent that is insoluble in the reaction mixture, right? Describe how the removal of a small quantity of water affects equilibrium. So here's the reaction, the same reaction that we're just looking at. And what this person is doing is removing water from the system, right? So let me hear your explanation. The system is already in equilibrium, right? And what you're doing is removing water. So how will the system respond? And why? The system will respond by increasing the amount of water, right? So which direction that corresponds to? Look at the equation. Which direction? Is it to the left or is it to the right? On which side is the water? Right. Exactly. So therefore, the equilibrium position will shift to the right in order to produce more water that has been removed. All right? So that's basically how Le Chatelier's principle works. All right. Okay, let's talk about heterogeneous equilibrium. So we're talking about situations where the different components are in different states. So the example that we're looking at here, I think we met this one before. Let me just write down the equation for this reaction. The equation for the reaction is calcium carbonate solid to form, calcium oxide plus carbon dioxide, CO2. Calcium oxide is a solid, carbon dioxide is a gas, right? So that's the equation, right? So what we're looking at here is a situation where we have calcium carbonate in an enclosed vessel. And then basically the calcium carbonate will initially decompose spontaneously. So you're going to have the formation of calcium oxide within the calcium carbonate and carbon dioxide, which would be, of course, a gas, so it will fill up the jar, right? And then you achieve equilibrium, right? So at this point here, B, the rate of the reverse and forward reaction would be the same. And then let's say you decide to add calcium oxide to this mixture, right? Well, what would happen is pretty much nothing as far as the carbon dioxide being formed is concerned. The amount of carbon dioxide formed would be fixed. And the reason why is because even though you add more calcium oxide, you're not changing the concentration of calcium oxide, right? So therefore, basically, the amount of carbon dioxide present above that mixture will be unchanged. The same is true if you were to add calcium carbonate for the same reason. Calcium carbonate is a solid. Even though you're adding more calcium carbonate, the concentration itself will not change. So therefore, the carbon dioxide being formed will not change either, right? So basically, the takeaway from this is that if you're adding or removing solids or liquids to a system already in equilibrium, that will not affect the equilibrium position, right? Doesn't change anything. It doesn't matter how much of either solid that you add in this particular case, there will be no change in the equilibrium position, and therefore the amount of carbon dioxide as reflected in the pressure will not change, all right? So that's something that you need to remember when it comes to heterogeneous equilibrium. Okay, let's look at another factor that will be explained by Le Chatelier's principle. And this deals with situations where gases are involved, all right? And we're going to look at two different situations here. We're going to look at one situation where, let's say you have a reaction and you only focus on one gas and you change the pressure of that gas. How will that affect the equilibrium position? And then the other situation we're going to look at are situations where the mixture is totally gaseous and how you change or how changes in the total pressure will affect the equilibrium position. So the first thing we're going to look at is you have a reaction and you only change the pressure of one gas. How will that affect the equilibrium position? Well, in order for us to understand that, I'm going to remind you of an equation that you should have met before. Certainly if you were in my class. Pressure is equal to, of a gas, is equal to the concentration of that gas times RT. Does that look familiar? Right, so what that tells us, if R and T are constants, well, R is definitely constant. If you hold the temperature constant, what that tells you is that the pressure is directly proportional to the gas, to the concentration of the gas, all right? So what does that mean? That means that what we discussed with respect to pressure changes and how they affect the equilibrium position can also apply to, what we said about concentration changes and how they affect the equilibrium position for reactions in a system of dynamic equilibrium. The same is true, or same can be said for pressure changes, right? So for example, let's say, I'm just gonna use this reaction as an example, just to illustrate this. So let's say, and these are all gases, nitrogen, hydrogen, and ammonia. These are all gases, right? So let's say you were to increase the pressure of nitrogen, right? This would imply an increase in the concentration of nitrogen, right? Because of what I just said here. Whatever the concentration is of the gas, that's directly proportional to the pressure. So if you increase the concentration of nitrogen, which direction will this reaction shift based on what we discussed before? If you all of a sudden increase the concentration of nitrogen, then what will happen? How will the system respond? We shift to you're increasing the concentration of nitrogen. We will shift to the right, because remember what we said, whatever you do to the system will try to counteract that change. So if you're increasing the concentration of nitrogen, the system will try to reduce the concentration of nitrogen, and it does so in this case by shifting to the right, all right? So basically, you're going to have an increase in the concentration of ammonia, an increase in the concentration of hydrogen, and a decrease in the concentration of hydrogen, and decrease in the concentration of nitrogen. So therefore, I'm going to say here that this implies that there will be a shift to the right, right? So that means that the concentration of ammonia will increase. The concentration of H2 will decrease. And the concentration of N2 will also decrease. All right? So that's basically how we deal with pressure changes for just one gas in the system, right? And of course, again, going back to this example, the converse or inverse is true. If you were to reduce the pressure of nitrogen, that means that the concentration of nitrogen would decrease, which means that the reaction will shift to the left to form more nitrogen, and the concentration of hydrogen would increase and the concentration of ammonia would decrease, all right? Okay, any questions about that? Any questions? All right, so I need to figure all of this here. And the next point here now is where we look at how changing the total pressure. Now this would apply to a totally gaseous system, right? And let's say you decide to change the total pressure. Let's say you decide to increase the total pressure. Then the question now becomes which direction or how will the system respond? Let's put it that way. Now, in order for us to answer that, we have to think of Le Chatelier's principle again. And basically, when the pressure is increased, what will happen is that the system will respond by trying to decrease the pressure. In this particular case, what this means is that this corresponds to an equilibrium shift, which produces fewer moles of gas, right? Now, in order for us to basically make that prediction, we have to have a balanced equation, and we have to look at the coefficients of the different gas molecules present in that system, right? And going back to the ammonia example, so let me rewrite this equation here. N2 plus 3H2 plus, to give 2NH3, right? So in order to make predictions as to what would happen when you increase the total pressure, what you have to do is look at the number of molecules represented on this side and compare to this side. So on this side, you have a total of 4 molecules of reactants, and over on this side, you have 2 molecules of products, right? So what will happen if you increase, write it here, if you increase total pressure, what will happen is that the equilibrium will shift to the direction that produces fewer gas molecules. In other words, will shift to the right. Because the right side has 2 molecules, the left side has 4, right? So therefore, the result would be that the concentrations of nitrogen and hydrogen would decrease. I'm sorry, let me erase this here. Okay, so I was saying the concentration of nitrogen will decrease, the concentration of hydrogen will decrease, and the concentration of ammonia will increase. All right? So that's what happens when you're trying to increase the total pressure of the system. The system will respond by decreasing the total pressure, which in this case corresponds to a shift in the direction producing fewer gas molecules, so therefore it will shift in this case to the right. And of course, again, the converse or inverse would be, you can figure that out as well. If you were to decrease the total pressure, then the system will try to increase total pressure by shifting in the other direction, which produces a greater number of molecules, all right? So therefore, in that case, the concentration of the reactants would increase and the concentration of the product would decrease, all right? Okay, any questions about this? Any questions? Any questions? All right, let me clear this and see what's next. So this is just describing the reverse, all right? Now, in some cases, if you write the equation and it's balanced, you'll notice that the number of molecules on either side will be the same. So what does that mean if you were to change the pressure? Well, the answer is that changing the pressure on such reactions will have no effect, right, on the direction, there won't be any shift in one direction or the other, right? Because if you have, in this case here, the reaction between hydrogen and iodine to form hydrogen iodide, if you look at this here, you have 2 molecules on this side, you have 2 molecules on this side, so therefore it doesn't matter what you do if you increase or decrease the pressure, no change, right? The reaction will not shift to favor either reactant or products, all right? Okay, so that's what happens when you change the pressure. This only applies, remember, to gaseous systems. So if there are any solids or liquids or aqueous solutions involved, this discussion in terms of changing the external pressure will not apply, right? It only applies to totally gaseous systems. Okay, so this is just demonstrating an example of this. Now, the equation for this reaction here is NO2 gas, two of these, to form N2O4, all right? So this is also a gas, all right? So basically, in this particular case, you have 2 moles of gases on this side, you have 1 mole of gas on this side. So in this case, what you're doing is increasing the pressure. So if you're increasing the total pressure, P total, right? Then the system will respond by decreasing the pressure, right? So basically the equilibrium will shift to the side which has a few gas molecules, so shift to the right, all right? So therefore what will happen is that the concentration of N2O4 would increase and the concentration of NO2 would decrease. And in this particular case, because of the difference in colors between these two substances, you can actually see the change, right? Because NO2 is a yellow-brown gas, yellow-brown gas, right? N2O4 is pale green. It's almost, colorless, but I'm going to put pale green here, all right? So in this particular case, if you were to increase the total pressure, right? Let's say you have the system already in equilibrium, and let's say the mixture is brown because you may have more of the NO2 molecules than the N2O4, right? And then when you increase the pressure, the equilibrium will shift to favor the formation of N2O4. What will happen in that case is that the mixture would look less brown and more, pale green or colorless, right? So you can actually, in some cases, see the color changes taking place, which basically can be predicted based on Le Chatelier's principle, right? And this is just basically representing what happens here when you increase the pressure from 1 to 2 atmospheres. What happens is that 2 of these molecules of NO2 will come together to form a molecule of N2O4, and therefore that's basically what happens. Let me see. Right, because it produces less molecules, which counteracts the increased pressure. All right, so that's basically what happens in this case. What time is it? Okay, let's go to the assignment. Let's see if we can do, okay, let me look at number 6 here. Okay, we can do number 6, all right. So they gave us this equation, right? And it says state and explain. So you have to explain now. And the explanation would involve Le Chatelier's principle. The changes in the equilibrium mixture or composition that will occur at a constant temperature if, and the first one is if the pressure or the concentration of N2 is increased, right? So this is a system right here. And let's say all of a sudden you increase the pressure of the N2. So let me hear what you have to say concerning what will happen and why. So let's think about Le Chatelier's principle. Whatever you do to the system to disturb the equilibrium, the system will do the opposite to restore equilibrium, all right? So the change being imposed on the system in this case is that you're increasing the pressure or concentration of nitrogen. So how will the system respond? It's going to shift to the right. So basically what you're going to say in your explanation is that the system will respond by shifting to the right and thereby reducing the pressure of nitrogen or the concentration of nitrogen. All right, the system is going to shift to the right thereby reducing the pressure or concentration of nitrogen. All right? Any questions about that? Any questions? Okay, what about B? B says you're increasing the pressure or concentration of NO. So how will the system respond? And I want to hear your explanation. It's going to shift in which direction? To the left. And why would it do that? Because you're going to reduce the concentration or pressure of NO, right? You're doing the opposite of what is being imposed. The system will do the opposite of what you're imposing on the system. All right? Any questions about that? Okay, what about C? You're increasing the total pressure on the system. How will the system respond? What do you look for whenever you're given that question about the total pressure? What do you look for? The number of molecules on either side. And what do we notice about this particular reaction? What's that? Exactly, they're equal, right? So what does that mean? There's no change, right? It doesn't matter if you increase or decrease the total pressure, there'll be no equilibrium shift because you have the same number of molecules on either side of the equation, all right? Okay, let me see what next comes up. Oh, now this one is interesting. It says, what happens if the total volume of the system is increased? Now, let me give you a hint to answer this question. What's the relationship between the pressure of a gas and its volume? What's the relationship between the pressure of a gas and its volume? If the volume of a gas increases, what happens to the pressure? The pressure decreases, right? In either case, the answer will still be the same as in the case of C, because again, if the pressure decreases, it doesn't change the equilibrium position because again, the number of molecules on either side are the same. All right, so the answer would be the same as in the case of C. No change because the number of molecules of gases on either side is the same. Okay, now E, we didn't get into this, but I can tell you the answer. We're going to talk about it later on, but basically adding a catalyst to a system already in equilibrium does not change the equilibrium position, right? And let me just briefly explain. I'm going to get into it in more detail. Well, I don't think maybe in this class, but the next class. Basically what happens is that when you add a catalyst to the system, as we learned in the previous chapter, the catalyst provides a different mechanistic pathway of a lower activation energy, right? So basically, adding a catalyst will increase the rate of reaction. In the case of a system in a state of dynamic equilibrium, adding a catalyst will increase the rate of reaction of both the forward and reverse reaction, right? So basically, both activation energies will be changed to the same extent. The rate of the forward reaction would be increased to the same extent as the rate of the reverse reaction, but the rates will still be equal, right? So therefore, as a result, no change, right? So the answer for E is no change, and that's because by adding a catalyst, the rates of both the forward and reverse reaction will change to the same extent, all right? And therefore, there'll be no change. We're going to talk about that in more detail later on, but that's basically the answer. Okay, and then now, F, decrease the concentration of O2. So let me go back to the equation here. Okay, so what will happen if you decrease, all of a sudden, you decrease the concentration of O2? Then the system will do what? Which direction will the system shift? To the left, right, exactly. And the reason why it does that is because the change you're imposing is that you're decreasing the concentration of O2, right? And the system will shift to the left to produce O2 because the system is responding by doing the opposite of what you are doing on the system. All right, so that's basically how we answer that. the system will shift to the left so as to increase the concentration of O2, which is the opposite of what is being done to the system. All right? Okay, and I think that's the last question. Let me just check here. Okay, that's the last question in that section. Okay, so let me go back to the PowerPoint and then we can finish up on our activity for today. So, all right, so here we're going to get into temperature changes, right? Another factor that would affect the equilibrium position. Now, again, Le Chatellier's principle comes into play. Whatever you do to the system will try to do the opposite, right? So in terms of temperature changes, if you try to increase the temperature on the system, then the system will try to reduce the temperature and vice versa. Now, the question now becomes, how will the system do that? In order for us to answer that question, we have to look at whether or not the reaction is either endothermic or exothermic, right? And I'm quite sure you're familiar with those two terms from your previous chemistry experience. But just to remind you, an exothermic reaction is one that produces heat energy, right? As you go from reactants to products. An endothermic reaction is a reaction that absorbs energy, heat energy from its environment, right? And in the case of a reaction that is exothermic, the enthalpy change, well, let me deal with endothermic first. In the case of endothermic reactions, delta H is greater than zero. What do I say? Greater than zero. This here is greater than zero. And in the case of exothermic reactions, delta H is less than zero, right? A change in enthalpy. All right? Now, in order for us to make predictions, right? What you can do, and this is a very useful tool in order to make these predictions, we can consider heat to be a product in the case of an exothermic reaction, and we can consider heat to be a reactant in the case of an endothermic reaction, and then we apply Le Chatelier's principle, all right? So, oh, I don't have an example here. Okay, let me make up an example. Let me get out of this here. And in fact, let me insert another slide. I'm going to go back to the ammonia example, the nitrogen plus hydrogen to give ammonia. N2 plus 3H2 to form 2NH3. Now, I know this reaction is exothermic. I don't know what the value is, but I know that delta H is negative, right? So what we're saying here, or what I was just saying, is that because we know this reaction is exothermic, we know that heat is produced. So another way of writing this is N2 plus 3H2 to give 2NH3 plus delta H. So basically the heat is seen as a product, right? Because it's produced in an exothermic reaction, all right? Now, based on that, we can make predictions as to what will happen when you either increase or decrease the temperature. So let's look at what happens when you increase temperature. So in order to increase temperature, what we're doing is adding heat, all right? So what the system will try to do is to remove the heat, right? The change you're imposing is that you're adding heat, the system will try to absorb the heat, and then what will happen is that because you're increasing the amount of heat, that means that the equilibrium position will shift to the left. So therefore, equilibrium position will shift to the left, right? So what will happen to the concentration of N2? The concentration of N2 will increase. What will happen to the concentration of H2? Will increase as well. And what will happen to the concentration of ammonia? Will decrease, all right? So that is basically what will happen if you increase the temperature on the system, then the system will try to decrease the temperature by removing the heat that is being added to the system. That means that it's going to shift in the endothermic direction, in the opposite direction to the forward reaction. And as a result, the concentration of the reactants will increase and the concentration of the product will decrease, right? And if you understand this, then you should be able to predict what will happen if you decrease the temperature, right? If all of a sudden you decrease the temperature, then that corresponds to removing heat, right? And then what will happen to the equilibrium position? Equilibrium position will shift to the right. And the concentrations of, what will happen to the concentration of N2? Will decrease, the concentration of H2 will decrease, and the concentration of ammonia will increase, all right? So that's basically what it comes down to in terms of making predictions as to which direction the reaction will go or shift when you either increase or decrease the temperature. The first thing you should look for is whether or not the reaction is exothermic or endothermic, right? Once you determine that it's exothermic, you put the delta H on the right, because if it's exothermic, then delta H or the heat is seen as a product. Now, if the reaction is endothermic, then you put the delta H on the left. Let me see if I can come up with an example of that. So an example of an endothermic would be N2O4 gas to form NO2, and you're going to need two of these. In this case, delta H is positive, right? In other words, going from left to right, heat is absorbed. So in this particular case, you can rewrite this as delta H plus N2O4 gas to give 2NO2, right? So once you write it like that, then you can make your predictions, right? If you increase the temperature or decrease the temperature, system will be either absorbing heat or releasing heat, and then you can tell which direction the reaction will shift and what will be favored, you know, what will be increasing in concentration, what will be decreasing in concentration, all right? Okay, so that's basically, as far as temperature is concerned, how the equilibrium system will respond. Now, one more thing I need to say about this, right? If you recall, I think I said this last class or maybe the class before. Remember I said that Kc is constant if the temperature is constant, right? The only factor that will change the value of Kc is temperature, right? And I think that point is being made in the next slide right here. Temperature is the only factor that would affect the value of Kc, Kp, and the other Ks that you're going to meet later on, right? Now, based on what we just discussed, I can tell, or you can tell, or you should be able to tell what happens to the Kc value in this case. Because, for example, remember I said here that when the temperature increases, the concentration of N2 and H2 would fall, and the concentration of ammonia, would increase, and the concentration of ammonia would fall. Now remember, Kc is equal to what? Concentration of NH3 squared divided by concentration of N2 times the concentration of H2 cubed, right? So if the concentration of N2 and H2 increases, and at the same time the concentration of NH3, so these two would increase, and the concentration of NH3 would decrease, then what happens to Kc? If these two denominator values increase and the numerator value decreases, then what happens to the Kc value? It will. If these two increases, the bottom part increases and the top part decreases, then what happens to the Kc value? Will it increase or will it decrease? Decrease, exactly. So the Kc value will decrease, all right? So that's basically explaining that, you know, temperature does affect Kc, all right? And temperature is the only factor that affects Kc, right? Not concentration, not pressure, not the addition of a catalyst. The only factor that would affect the value of Kc would be the temperature, all right? Okay, what time is it? Oh, 5 more minutes. Okay, let's look at these two examples and then I'll call it a day, all right? So the first example, they gave you an equation which is balanced, and the question says it's at equilibrium initially, and then you transfer that mixture from a 1 liter flask to a 2 liter flask. So the question is, in which direction will the reaction shift in order to restore equilibrium? All right? Now, what happens when you go from 1 liter to 2 liters in terms of the gases? What will change? The overall what? If you suddenly increase the volume of a container containing a gas, what change will take place in the gas, apart from the increase in volume? The pressure, right? So basically, if you're increasing the volume of the gas from 1 liter to 2 liter, that means that the pressure of the mixture will decrease. So you're reducing the total pressure of the mixture. So the question now becomes, how will the system respond to that based on Le Chatelier's principle? The system will respond by
Doing the opposite of what it's doing.
It's going to do the opposite, exactly, increase the pressure. So how will the system increase the pressure? Which direction will the equilibrium shift in order to increase the total pressure? Shift to the what? Left or right? Let me give you a hint. This has 2 molecules on this side, and this has 3 molecules on this side. So which direction do you think the reaction is going to shift in order to increase the total pressure? To the right. All right? So therefore, that's the answer. The answer is that it's going to shift to the right, because by doing that, it's going to increase the number of molecules and therefore increase the total pressure. All right. The next example, give you the equation, and the question gives you delta H, right? That's a hint right there, right? So the question is asking, is the amount of NO formed from given amounts of N2 and O2 greater at high or low temperatures? So in other words, the question is asking whether or not a high temperature or a low temperature would favor the formation of NO. And the hint lies right here. So what I would do, since we know that the reaction is endothermic, I would rewrite the equation and put delta H here. In other words, the heat will be seen as a reactant, okay? So based on that, which would favor the formation of NO? Would it be high temperature or low temperature? High temperature, because for high temperature, that means that you have to add energy, heat energy. And the system will try to reduce that amount of heat energy present by using it up and shifting to the product side, and therefore that would favor the formation of NO. All right? So basically, the answer would be high temperatures. All right? Okay, I think I'm going to stop here for now, but let me just say this. So there's a lot of applications to industrial medicine when it comes to Le Chatelier's principle, because as you can see, changing conditions can favor the reaction going one way or the other. So if you can imagine yourself in a situation where, okay, somebody has their, oh, that's you? Oh, okay. So, you can imagine yourself in a situation where you know what the reaction is, and let's say you're employed to favor the formation of a particular product, then you have to take into account whether or not the reaction is exothermic, if it's a gaseous reaction and all that, and then you can choose the conditions that would favor your product that you're trying to isolate. So that's where the application of Le Chatelier's principle comes into place, in industry especially, all right? Okay, I'm going to stop here, but there's something I have to say which I completely forgot. Your test next week, right? So I have, somebody's asking a question here. Oh, yes. Thank you, Ms. Macias. I'm about to mention that as well. So your test next week will be based on chapters 1 and 2. And I have sent you guys the graded assignments for chapter 2 this morning. I've also posted the answer keys, right? So I would strongly suggest that you review those. Also review the past tests that I've posted. And I would strongly suggest that you try as many questions from your textbook as possible, all right? And if you have any problems or if you need me to explain anything, then please contact me concerning that. And as Ms. Messias just reminded me, the event that will be held in Building 2, you're cordially invited to attend. And I think I'll be giving some extra points for those of you who attend. So I'll be providing a sign-up sheet for those of you who are there in person. You can also attend, of course, via Zoom. I've provided a link for the Zoom link. So you can attend that way as well. And also that would be recorded. Your presence virtually will be recorded that way. Yeah, you had a question?
Oh, no.
Oh, okay. All right, so that's pretty much it. So I'll see you guys next week, Monday.
Yes.
Because the change that you're making is that you are increasing the concentration of alcohol in the system, which should be right, to decrease the concentration of alcohol. Right, the system will do that for them. Oh, my bad. This is N2. So yes, this will be shifted to the right. And then in the case of NO, it's going to shift to the left. Yeah. Okay, so if you decrease the concentration of O2, the equilibrium will shift to the left in order to produce more O2. So the key thing you need to remember is that whatever you do to the system will respond by doing the opposite. Because you see, what you did to the system is disturb the equilibrium. And the system is going to try to restore equilibrium by doing the opposite of whatever change you impose on the system.
To the left,
Yeah, in that case.
decrease in oxygen.
Well, yeah, because the oxygen is being decreased, so the system will try to increase the oxygen by shifting to the left. All right?
And do you still want me to take photos of that event?
I'm sorry?
You still want me to take photos?
Take what?
Photos of the event?
Oh, yes, please.
Okay.
I would really appreciate it.
And how long is it last for?
It depends on the speakers, actually. I basically, in planning this, I basically arrange for everything to end at 2:00. So it depends on the speakers. I don't know exactly the length, but I don't think it would take up all of that time, so. Yes, sir.
I have a couple questions about my grade for assignment 2.
Uh-huh.
During your office hours for that?
Yeah, I'll be in my office today from, today's Wednesday, 2 to 6. All right, 2 to 6. But you're talking about what now?
The assignment 2. grade.
Oh, okay. So did I send you
Yes,
the?
yes, you did. It's
Okay.
just-
So, all right, we can talk about it. Yeah, we can talk about it. Let me get over.